Okay, here is your video lecture for Chapter 4, Section 3. It's going to be the last section of Chapter 4. It's called Electron Configurations. Now, this is going to be a fairly tough concept to get at first, but once you get it, you'll be able to flow like a river. It's going to be very easy once you get that aha moment. So just hang in there and do what you can when you can. First off, let's review a little bit from last section. Talked about subshells being represented by letters S, P, D, and F, and we had a certain number of electrons that were associated with each subshell. S subshell has a maximum of 2 electrons. Any P subshell has a maximum of 6 electrons. Any D subshell has a maximum of 10, and any F subshell has a maximum of 14 electrons. And that's true for any energy level. N equals whatever, that particular subshell will have that associated number of electrons. So let's see what we remember from last section. Looking at the periodic table ahead here, I have a few elements that are highlighted. What subshell is being highlighted in the periodic table above? Pause the video until you can come up with an answer. I hope you selected 5P. Looking at, we have n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. This is the fifth period. Here's the fifth period. Then this is the P block. So this is 5P. Moving on, an electron is an S or in an S suborbital, has the following approximate geometry. Please pause the video until you can come up with an answer. Correct answer is C, a spherical orbital. All S suborbitals have a spherical shape, more or less. Go ahead and pause the video until you can come up with an answer. In magnesium atoms, the number of electrons in the third shell will be 2. Okay, it's in the second family, second group, so that the second electron is filling in to that spot. Go ahead and pause the video, and I would like you to fill in all of these blanks with this word bank down here at the bottom. Go ahead and pause the video until you can fill all those in. Here we go to complete this sentence. 2 electrons fit in the 1 orbital of an S sublevel. S sublevel has 1 orbital. 6 electrons can fit in the 3 orbitals of a P sublevel. 10 electrons can fit in the 5 orbitals of a D sublevel. And 14 electrons can fit in the 7 orbitals of an F sublevel. So on to some new stuff, electron configurations. The quantum model improves on the Bohr model because it describes the arrangements of electrons in atoms other than hydrogen. That was the one shortcoming of the Bohr model. It really only highlighted or spoke about hydrogen. The arrangement of electrons in an atom is known as the atom's electron configuration. How the electrons fill in around the nucleus has a specific shape, and it's very predictable. We call it the electron configuration. Electrons in atoms tend to assume arrangement that have the lowest possible energy, and this is going to be a very important idea as we go along. We have to find the lowest possible energy, the most stable, the thing that approximates the ground state. And the low energy arrangement of electrons for each element is known as that element's ground state electron configuration. So this is just a general mapping of the periodic table. We see that these two groups over on the left are the S block, including helium over here. He's kind of lonely. But we have everything over here. This is the S block. Okay, we then move to the P block. Once we get down to n equals 4, we can start entering the D block. We have to get down to n equals 1, 2, 3, 4, 5, and 6 before we start seeing some F block action. But these, everything here, any electron filling into these atoms are associated with these letters: S block, D block, P block, F block. Getting a little bit more specific, you can see that hydrogen, the electron that is in hydrogen fills the 1s orbital, and then the 2 electrons in helium are also filling the 1s orbital. If we have one more electron, okay, that, to balance out our third proton to make lithium, that third electron has to fill into the 2s orbital. The fourth electron will fill into the 2s orbital. But a fifth electron will move up into the 2p orbital. And on and on and on and on and on. Notice how the number in front of the s here is always in the n value. N equals 1, 2, 3, 4, 5, 6, 7. But that is not the case for D. When n equals 4, that's the 3D. When n equals 5, that's 4D. When n equals 6, that's 5D. And when n equals 7, that is 6D. Just a little thing you got to get used to, and you will get used to it as long as you attempt the practice. Alright, so we're going to go over rules, and there are set rules that if you can remember this small number of rules, about 4, you're going to be able to do this just fine. So first rule we're going to talk about is the Aufbau principle, and Aufbau is just German for building up, so don't be intimidated by that. That's not somebody's name. So according to the Aufbau principle, or the building up principle, an electron occupies the lowest energy orbit that can receive it. Okay, if there's a low energy orbit, then that electron is going to fill that one instead of some higher energy level orbital. The orbital with the lowest energy of all the orbitals is the 1s orbital. The 2s orbital is the next lowest, and then the 2p. And the energies of the sublevels begin to overlap, starting with the third main energy level. You get a clearer idea of what that means looking at this diagram. Now, on the y-axis here, we have energy level. Okay, how much energy an electron has to have in order to fill this orbital. 1s being the lowest energy, moving up. The 2s is the next highest here on the y-axis. Next furthest up is the 2p. Going up again, we get 3s. Going up one more, 3p, then 4s, and then 3d. Now, the space on this y-axis is relative. So you notice that there's a big energy difference between 1s and 2s. But the energy difference between 2s and 2p is not that significant. And then moving up, the difference between, for example, 3p and 4s is not that significant. Compared to the difference between 2p and 3s, it's a much smaller difference. And this actually will come into play when we learn about hybridization later on. But what I'd like you to do right now is pause the video and list all of the orbitals that you see on this diagram in order from lowest to highest energy. Please pause the video and do that now. 1s is the lowest, 2s next, then 2p, then 3s, then 3p, then 4s, and then 3d being the highest energy level that's present on this diagram. There are higher energy levels, just not on this diagram. Moving on to the second rule. This has to do with the spin quantum number. According to the Pauli exclusion principle, that's our second rule, an orbital can hold 2 electrons of opposite spin. And the two values of the spin quantum number allow the 2 electrons of opposite spins to occupy the orbital. So each orbital can have 2 electrons. Okay, that's fair enough, but they have to have opposite spin. So I have 2 potential 1s orbitals over here, each represented by this red box. In one, I have an electron represented with an up arrow and an electron represented by a down arrow. The electron with the up arrow has an up spin, and the arrow right here is a down spin. My other option is 2 electrons with both having up spin. Which one is plausible? Alright, according to the Pauli exclusion principle over here, an orbital can hold 2 electrons. That's fine, they both have 2 electrons, but they have to have opposite spin. One needs to be up and one needs to be down. So this orbital with 2 up spin electrons is not possible. The third rule requires placing as many unpaired electrons as possible in separate orbitals in the same energy level. Now, it sounds like a lot, but once you see it in a diagram, it won't be that bad. So in this way, electron-to-electron repulsion is minimized so that the electron arrangements have the lowest energy possible. This is called Hund's rule. So again, according to Hund's rule, orbitals of equal energy. So for example, we have different p sublevels here. Now, this might be a 2p, or 3p, 4p, whatever. These are all p orbitals, so they have the 3 sublevels. Okay, 3 sublevels here. According to Hund's rule, orbitals of equal energy, okay, 3 orbitals here, they're all the same energy, they're all p orbitals, are each occupied by 1 electron before any orbital is occupied by a second electron. And all electrons in a singly occupied orbital must have the same spin. Okay, so with the first example right here, we see that there is 1 electron with upspin. That's fine. And just by convention, just FYI, we do always draw the first electron as having upspin. That's not the case in real life. This is just convention that we always draw upspin first. It could truly be downspin, but as long as all of the electrons in singly occupied orbitals have the same spin, that's actually fine. So, if we were going to start filling this p orbital over here, okay, this first sublevel, what spin would that first electron have? It would have upspin. Okay. Now, if we were to add a second electron to this orbital, this p sublevel, this p orbital right here, where would the electron go? In this sublevel, this sublevel, this sublevel. It would go into this second available empty orbital right here instead of pairing up. And then thirdly, we have our third electron would go into the other open area before it would pair up. Now our third situation down here, we have a p orbital that has 3 electrons already. They can have a maximum 6. It already has 3. So where is this electron going to go, and what spin is it going to have? It's going to go back and start to pair up because there are no other open orbitals, and it has to have an opposite spin. Alright, so applying those 3 rules that we just looked at, as we add electrons to our atom or electrons to our system, we're going to add them in this fashion. To the 1s orbital first, upspin, then downspin. To the next highest energy level, which is 2s, upspin, then downspin. Then our next highest energy level is 2p. We'll have upspin, upspin, upspin. Before we start pairing up, downspin, downspin, downspin. To the next energy level, 3s, upspin, and then downspin. To the next highest energy level, which is 3p, upspin, upspin, upspin. And then let's start pairing up, downspin, downspin, downspin. 4s, upspin, downspin, and then 3d, upspin, 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 upspin. And then let's pair them up. Alright, so make sure you copy this down. And go through the process here of writing down all your upspins first before you go back and pair them up. It's just a good habit to have. Let's check for understanding so far. Go ahead and pause the video until you can come up with an answer for this question. Alright, correct answer is D, off bow. Next check for understanding. Go ahead and pause the video. What is Hund's rule? Electrons will enter empty orbitals of the same energy level, before pairing up in an orbital with an electron already present. Next check for understanding. Please pause the video. Which of the rules discussed in this lesson relates to the spin of an electron in an orbital? Hund's rule. Moving on. How do we represent? Okay, we know these rules for electron configurations, but how do we represent them or communicate them to other people? There are 3 main methods that are used to indicate these electron configurations. They are orbital notation, Electron-Configuration Notation, and noble gas notation. We're going to go through those 3 right now. In orbital notation, an unoccupied orbital is represented by a line. It's just a blank line, with the orbital's name written beneath the line. An orbital containing 1 electron is represented by an up arrow, upspin. An arrow containing 2 electrons is represented by an up arrow and a down arrow, showing the electrons are paired and they have opposite spins. So here's some examples. So you have hydrogen. Okay, this is a balanced hydrogen atom, and for all these examples, unless otherwise noted, they're going to be electrically balanced. So however many protons an atom has here, it's going to have that same number of electrons. Hydrogen, 1 proton, we assume 1 electron. So it has 1 electron to fill. It goes into the lowest energy level, 1s. That's an upspin. Helium, 2 protons, 2 electrons to fill. We can fill up the 1s orbital and we're good to go. So how about you try this one? Pause the video and see if you can come up with an answer for this. Alright, give the orbital notation for the ground state electron configuration of O. That's oxygen. Hope you selected D. Notice that we have opposite spins on all of our electrons here. C has some same spin electrons. Let's see. Yep, that was the big no-no here. Okay, they all have to be opposite spins. Alright, here's a fourth rule that's getting a little bit ahead of ourselves, but it's going to be useful for you. It's called the Octet Rule, and it states that the first shell, okay, n equals 1. Okay, so that's going to be elements like hydrogen and helium, and that's it. So the first shell can hold up to 2 electrons, a duet, but each shell thereafter can hold up to 8 electrons, known as an octet. So it's represented here in this diagram. We have hydrogen here, atomic number of 1 proton. It has 1 electron, but it has room for 2. Once that first shell, n equals 1, is full, you're going to kick up to n equals 2, and this n equals 2 orbital can have up to 8. Here, okay, in carbon, atomic number 6, that has 6 total electrons, 2 in n equals 1 shell, but in n equals 2, there are 4. So it actually has room for 4 more. Here's an example with nitrogen, and here's an example with oxygen. So again, n equals 1, hydrogen and helium. It takes 2 electrons to fill this first shell. 1, 1, 2, and then now we have to fill 8. We have to fill 8. This is 2s, 2s1, 2s2, 2s3, 2s1, 2s2. And then we're into the 2p, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. Alright, let's see how we're doing. Go ahead and pause the video and see if you can answer this question. How many electrons can fit in the first energy level? That's 2. Moving on to the electron configuration notation. We just did the orbital. Okay, the orbital notation. This is the electron configuration notation. Electron configuration notation eliminates the lines and arrows of the orbital notation. Instead, the number of electrons in the sublevel is shown by adding a superscript to that sublevel, that letter designation. So instead of arrows, we're just using superscript numbers. An example would be hydrogen, whereas we had on the 1s, we had an up arrow, and that was it. We go 1s, 1. For helium, in that same 1s orbital, we had a up arrow and then a down arrow. Here we have 1s, 2 to signify that it has 2 electrons in that 1s orbital. And we have to assume, because of the rules we learned earlier, that those electrons are going to have opposite spins. So remember that periods are horizontal on the periodic table. And according to the off-bout principle, after 1s orbital is filled, the next electron occupies the 2s orbital. The highest occupied level is the electron-containing main energy level with the highest principal quantum number. Okay, so n equals whatever, wherever that last electron is, that's the highest occupied level. The inner shell electrons are electrons that are not in the highest occupied level. For example, if lithium is 1s2, because it has 2 electrons in the 1s orbital, and then 1 electron in the 2s orbital, the highest occupied level is 2s, and the inner shell electrons are the 1s2 electrons. Electrons will pair up before jumping to the next energy level, for sure. Moving on to the third period, n equals 3. After that outer octet is filled by neon, or in neon, the next electron jumps to the third main energy level, n equals 3. Sodium is that first element that we find, and the electron configuration is 1s2, 2s2, 2p6, 3s1. Notice that everything in the third period starts with the series 1s2, 2s2, 2p6. Everything in that third period, everything across the periodic table in n equals 3, or the third period, starts with that same sequence. This allows us to move into our next and final notation that saves us a lot of time, called the noble gas notation. We'll get to that in a second. Let's check to see how we're doing with the electron configuration so far. Pause the video and see if you can come up with an answer. Alright, I hope you picked A here. That is sodium. That's actually what we just used in the example. Okay, 1s2, 2s2, 2p6, 3s1 is sodium. Go ahead and pause the video and see if you can come up with an answer to this harder one, referring to chlorine. Alright, I hope you selected B, 1s1. I'm sorry, that should be... Oh, we got this double represented. Oh, uh-oh. Okay, just scratch this guy out right here. 1s2, 2s2. Nope, I selected the wrong answer. I'm sorry, everybody. That is not right at all. Huh, ignore this one. Oh, goodness gracious. On to noble gas notation. The group 18 elements. So that's the noble gases on the far right side of the periodic table. We're going to use these in order to simplify our notation. So when we move to a new energy level, okay, N goes up by 1. We're going to use the previous noble gases symbol and then add the remaining electron configuration. Make sure you have your periodic table handy here and look at sodium. The previous noble gas was neon. Sodium has all of the inner shell electrons that neon has, plus an extra 3s1 electron. And so we're going to denote sodium by putting Ne, neon, in brackets, and then 3s1. That's sodium. Argon, the next noble gas here, can be represented by, again, neon in brackets because it has all those same inner shell electrons, and then 3s2, 3p6 to get all the way back to the electron gas configuration. A noble gas configuration is an outer main energy level that is fully occupied, and in most cases with 8 electrons, as per that octet rule. Now, here's where the electron configuration gets tricky. Everything else is pretty straightforward. At the 4th period, the 4s sublevels are filled first, the 3d sublevels next, and then the 4p sublevels. Even though the 4s fill up before the 3d, if the 3d are occupied, we write them first. For example, got potassium, okay, we got 4s1, 3d6, 4s2. Alright, so it's just a little thing about convention right there, just to keep in mind. Alright, here are a couple of checks for understanding for you. Go ahead and pause the video and see if you can come up with an answer. I hope you selected B there. Okay, the krypton's inner shell electrons plus 2 5s electrons, 10 4d electrons, and 2 5p electrons. Exceptions to the rule. There are exceptions. Chromium has an electron configuration of argon and then 5 3d electrons, not 6. That 6th electron is actually in the 4s orbital. Now, according to all the rules we've learned so far, is that 4s electron should be in the 3d orbital, but that's just not the case. There is reasoning behind this. It does make sense, and it can be predicted because it turns out that this arrangement requires less energy for chromium, and that's always the big push here for stability, low energy. There is an explanation, but we are not going to push it hard in this class. Chromium isn't the only explanation. The only thing I want to point out to you is that I will not give you an exception to solve on a test unless I tell you specifically that it is an exception, and I'll be asking you to reason that out. But that will definitely be one of the higher level questions here, and we'll practice that in class. All right, lastly, the progress of filling up sublevels along the 6th period is the 6s, and then the 5d, then the 4f, then 6p, but the 4f will fill up before the 5d. The energy levels between the 5d and the 4f are very, very close, and that's why there are many of those deviations from what you would normally expect, a lot of those exceptions to the rules. Now, the 7th period is not complete because it's mostly made up of man-made elements, and you are not going to get electron configuration questions from that period in this class. When you move on, start taking higher level chemistry classes, you might, but not in this class. I just want you to make you aware that there are some exceptions to the rules. All right, I will see you next period.